Okay, hey class, Mr. Bean here. We're going to go over pre-lab 11, the egg drop for AP Physics. And on this lab here, we want to make sure we have a principal investigator who will be documenting the events of this lab. And here's partners 1, 2, and 3. And the overview. We will substitute a toy globe for our initial trial. Okay. The objectives of the lab are to determine acceleration of the globe, which should be about 9.8, velocity at the moment of impact, and time. Okay, we have too many times on here, and time to impact. Okay, time to impact. Students in groups will assign one member to use a smartphone to video record the event. I also have a camera or an iPad you can use as well. Then the other students will try to take the time by external timing device and take the average value. The student with Mr. Bean's assistance will use video editing software to determine actual flight time and compare the average time values. And we want to compare the results of acceleration with the accepted value of 9.8 meters per second squared. All right, so here's a theory that you probably want to take written notes and then do a screenshot, but I'll have it on the end of this video here or on this document, which I'll upload to Google Classroom. Materials and data table. Again, maybe create your own data table on paper, insert screenshot. Now, the reason we're doing this is that I have a suspicion with the COVID situation that we may end up having to do remote AP testing like we did 2 years ago, just in case. Okay. Error analysis, okay, individually done. Okay. Insert screenshot. And then procedure. We're going to do this at the end. Okay, I want you to, once the lab is complete, review your notes and write a procedure on how you would do this. So we're going to be doing the procedures at the end of the lab. Okay, and conclusions. Were the objectives met? Any improvements? Okay, don't say this was a fun lab and we had human error. Okay, that's not going to cut it. Okay, okay, so theory. So right here, we'll call this theory here. Now go ahead and write down here theory, and we will see what is going on. Okay, so theory. So we're going to go senator square. So senator square here. I'm going to write down senator square. Okay. And so here's this bridge or the railing in Senator Square, and here's the bottom of Senator Square right here. Now there's a brown railing, and let me use, oh, I even have brown. Okay, so we're gonna go here, and there's this brown railing. Okay, okay, there's a brown railing there. Okay, everyone's familiar with the brown railing. Okay, and that's important that we understand the brown railing. Okay, so a couple of things here. The brown railing. Okay, so I'm gonna kind of like from here. So the brown, we're going to use delta y since we're talking about vertical motion, vertical movement. From the top of the brown railing to the floor, it's exactly 5.2 meters. Okay, we actually measured it one time. It is 5.2 meters off the ground. Okay, so from the top of the brown railing to the bottom here is exactly 5.2 meters. Okay, all right. So a student. One student will be up here, standing here, safely standing here, right? And they're going to be like, so here's the globe. Okay, okay. So this will be the globe. Okay. Okay, so you want to make sure the globe is at the bottom of the globe at the same height as the top of the brown railing, because we want to make sure we drop it 5.2 meters or close to it as possible. Okay, right. Other students, other lab members. Okay, okay. One person will be here. Okay, with the video. This person will video tape the event. Okay. Now, some people can do it in slow motion, but just do it in normal time, and we'll use the video editor software to get the actual time. The other team members may be over here, right? And they have their phone out too as well, and maybe a person here. Okay, okay. These people here will be the timers. Okay, the timers. Okay, all right. So whoever the video person is right here, this is the video person right here. Okay, so we're gonna do a bubble. Okay, they're gonna go 3, 2, 1, drop. Okay, So whoever's doing the video is going to tell this person up here, 3, 2, 1, drop. They're going to drop the globe, and these people will time best they can. Okay, so the globe is going to fall like this and gain speed. Right, it's going to be gaining speed here, and it's going to hit the ground. Okay, like so. Okay, so it's 5.2 meters above here. Now, consequently, what is the initial velocity? Yeah, it should be zero, right? Yeah. So, okay, so prior to impact, we want to know what is the velocity prior to impact, okay? And we also want to know what is the time duration here? What is this delta t? So, those are things that we want to find out throughout this experiment, okay? All right, so off to the side over here, we'll have some equations over here, right? All right, now we're talking about vertical motions. Now, the same equations we used before, we will now use for vertical motion. So in particular, we're going to use delta y. Okay, here's delta y is equal to VO. Now I'm going to use y here to show that we're talking about vertical motion here. There's t, right, for time. Now, because now g is going to act in what direction? Downwards, right? Now, because G is going downwards, so our frame of reference, so this is, we'll call it our frame of reference here. I forgot to put this down. This is our frame of reference. Because we're starting from rest and free falling, we will consider everything going down to be positive in this scenario. Okay, positive. Okay, that means G will have the positive value of 9.8 meters per second squared. Okay, so here we have plus 1/2, and okay, and here we're going to have. So I'm going to put this off to the side for right now. Okay, okay, a t squared. Okay, all right. So here's our. There should be a squared here. Okay, all right. So our equation here. What's zero here? Yeah. So this term here is going to be zero, right? So we will have delta y is equal to 1/2 a t squared. Okay. All right. Now, our objective is to figure out what is a. Okay. What's one of our objectives is to find out what is a. So can I solve this for a? So this is going to be 2 times delta y, right, is equal to a divided by, was it t squared, right? Okay. And I can simplify it some more because what's delta y? It is 5.2 meters, right? So we could do 2 times 5.2 uh, divided by t squared, right? And that should equal a should be what, 10.4? 10.4 divided by whatever our time is. Okay. So where should we get our time from? Yeah, from these guys here and from the video software. Now, is there going to be some error with these over here? Yeah, because stopping and starting. So when we do the video software, we can minimize the error dramatically. So this is how we're going to calculate our acceleration here. Okay, so this a should be fairly close uh, to our so g, which is 9.8. Okay, now our second objective is time. Okay, so we should be able to get the time. Okay, now our third objective is to find velocity prior to impact. Okay, now there's a couple of equations we have. We have this equation here. We have v squared equals vo squared plus 2. This should be y right here, right? Uh, 2 2 times a delta y squared. We have this equation. We also have v is equal to voy plus at. Okay. Okay. Could we use both these equations, or one of the equations, or neither of the equations? Well, yeah. Yeah. If I have time and the acceleration, I can use this equation here. Okay. So here I don't have time, but I do have acceleration and I do have delta y. So I should be able to do this, and these, should be fairly close. Okay, so I could either use this equation here, but I probably want to use this one here because I do have time. And then maybe compare it to this equation here, and maybe have some discussion as to why or why not they're the same. Okay. All right, so that is the gist of the experiment for today. Okay, that's pretty much it. So this here will kind of be the theory part here. Maybe take a screenshot of this here, and maybe make it a little bit smaller here, and uh, so this maybe rewrite the theory here, and so on and so forth. All right, let me go ahead and hit stop here, and then we will upload this for future use.